Hello everyone, I'm Dipinti Manandar from IIT Jodhpur. I'm Tech second year. So today I'm going to give a short presentation on the paper entitled Making Edge Computing Resilient. The authors of this paper are Yontam Harkole, Aisha Mustaq, Vivian Fang, James Macaulay, uh, Arujit Panda, Scott Schenker. The paper link can be found here. So, going towards the problem statement of the problem statement, the edge computing is being increasingly popular. There are multiple companies which are offering edge computing and storages. The main problem is edge fault tolerance. Session shares fate with a stateful edge. If edge fails, the session also fails. So recovering from the edge failures is trivial when the edge is stateless. The stateful recovery can be challenging as we can end up in an inconsistent state and it can take a long time to recover. So, to overcome the problems, the solution the authors have provided is provided are provided. I'm going to discuss it now. The edge fault tolerance is different as unlike data centers, the edges have limited resources. There are a lot of edges and we cannot scale all of them. When the entire edge fails, it is too expensive to provide adequate power and computations. Therefore, the ideal solutions are consistent recovery, survivability, and low overhead and quick recovery. Therefore, for consistent recovery, the recovered state should be consistent with the absorbed behavior by the client or server. The client keeps a log of all its outgoing messages and the server keeps a log of all of its outgoing messages. The edge sends periodic snapshots to the client or server. By receiving incremental updates and snapshots, the records of any observable behavior ensures consistency. So, if we are storing the logs at client and server, restores faith sharings, this ensures survivability too. Now going towards the novelty of the paper, the client edge server stateful network application, that is Cessna. The authors have provided a solution by creating a Cessna framework. It is designed to provide edge fault. It is helping towards the tolerance for stateful session based applications. The authors have built two types of prototypes. One uses Docker containers for checkpointing with edge logic in Python, which is easy for adoption, and other uses explicitly checkpointable data structures with edge logic in Rust or C Sharps, which is optimized for performance. The local recovery and hot recovery has been optimized. Going towards the critics, the paper proposes a resilient mechanisms but haven't done any careful experimentation evaluation on how it improves the resilience. It is language specific. It supports only C Sharp and Rust language. Therefore, it hinders in adoption. If there are a lot of failures, then the delays might be intolerable. Even though strongly stateful edge computation is already in use, its correctness and reasonable performance under failure and mobility is typically not guaranteed by the current approaches. Now going towards the scope of improvement, there must be careful experimentation evaluation on how to improve the resilient. It should be flexible for any programming languages, not only C Sharp and Rust, so that it won't hinder in adoption process. The number of failures must be decreased so that the delays could be tolerable. Even though strongly stateful edge computation is already in use, its correctness and reasonable performance under failure and mobility is typically not guaranteed by the current approaches. Now, lastly, going towards the schematic diagram, the author have produces a general design of framework which can be seen here. So, let me discuss more about it. When moving to a new edge, we need to ensure that before this new edge processes new packets from the client or server, it has established the last committed state of the previous edge. When the edge knows which message it has sent, only the client and server knows which of these were received. In addition, only the edge can capture the state needed to resolve non-determinism in its process of messages. All of this information must be effectively and efficiently combined to accomplish the faithful restoration of the last committed state in the new edge. The framework that the authors have designed consists of two portions, the edge platforms and the client server platform. In the Edge Application API that the authors have designed provides the methods which can be seen in this table. The framework maintains connection to both client and server. It runs a control loop that continually reads available data from these connections and triggers the appropriate event handler as described. Based on the application configuration, the underlying framework may, after it has finished handling an incoming message, request that the edge agent take a checkpoint of the application. The framework waits until the checkpoint is taken before reading and handles the next message. Now let's go to this client and server platform. There is a very little difference between client and server. A host, either client or server, is just an application running on the top of the host platform, which manages communication with the edge. The host platform consists of host agent and a connection handler. The host agent is responsible for edge discovery, establishing a session with the edge and its management. In case of an edge failure or client migration, it is responsible for re-establishing the session through another edge. The connection handler encapsulates outgoing packets to add the Cessna data plane header, buffers these messages, decapsulates the incoming message, and stores the received interleave log. In client-server application, the client does not directly connect to the known server, but it connects to an edge, potentially many edges. So determination of which edge to connect depends on the application, client and edge location and other factors. There are other discovery techniques like DNS or IP Anycast, which can be used for this purpose. So, mainly this paper mostly discuss about how to make the edge computing more resilient. Thank you.